let's imagine we have a container of our ideal gas, and it's in this container with a piston at the top, and let's imagine that that piston can move up and down. So we could push the piston down. If we wanted to decrease the volume of the gas, we could allow the piston to go up if we wanted to increase the volume of the gas. So in general, we could change the volume. We might put a weight on the piston to make more pressure on the gas. We could remove weight off the piston to make less pressure on the gas. So we can affect the pressure on the gas, allow it to increase or decrease. We might put a flame under this and heat the gas up to raise the temperature. We might surround it with ice or something like that to cool it down, to decrease the temperature. So let's imagine that we can change all of these quantities, the pressure, the volume, the temperature, but let's assume that we're not going to allow any gas to escape, nor are we going to put any more gas into the container. So we're going to assume that capital N and little n, the number of particles and the number of moles, are held constant. We're not going to change the amount of gas. Now I want to look at three different processes that we can do to change these other quantities of the gas. Now the first process, we're going to assume that whatever happens, we always bring it back to the same temperature. We don't allow the temperature to change. If we do something to the gas and it starts to heat up, we cool it down to bring it down to its original temperature. If we do something to the gas and it starts to cool down, we heat it back up to bring it back to the original temperature. So whatever happens, we're going to assume the temperature is held constant. This type of process is called an isothermal process. Iso means a constant thermal temperature. Isothermal means constant temperature. Now, let's go back to the ideal gas law. We have that PV equals NKT, or you could write it as little nRT if you want. Now let's look at the right side of this equation. We know that N is not going to change. We've already made that statement. We know that T for an isothermal process is not going to change. T is going to be held constant. And K is already a constant. So what do we know? Whatever we do to this gas in an isothermal process, the right side of this equation is not going to change. It's going to maintain a constant value. But if the right side is equal to the left side must also maintain a constant value. So no matter how we change the pressure and the volume for our isothermal process, the product of P times V must remain the same. So in other words, if we start out with some initial values, say P1 and V1, and we perform this process and end up with some final values, P2 and V2, we know that P1 times V1 must equal P2 times V2. So this condition must be true for an isothermal process. This is called Boyle's law. So for an isothermal process, we know that P1 V1 must equal P2 V2, where you can think of P1 and V1 as the initial pressure and the initial volume, respectively. P2 V2 are the final pressure and the final volume, respectively. Okay, let's stick some numbers in here. Let's imagine that we start out with a gas with an initial pressure of 1 atmosphere and an initial volume of 0.5 cubic meters. And then our final volume is 1.75 cubic meters. Let's figure out what is our final pressure. Well, first of all, let's just think about it for a second. Imagine we have this volume, this container, and our initial volume is 0.5 cubic meters. Our final volume is larger. It's 1.75 cubic meters. In other words, we're allowing the volume to get larger. The gas is expanding. What would we expect to happen to the pressure? Would we expect the pressure to get larger or smaller? Well, if we increase the volume, we would expect the pressure to get smaller. If the temperature of the gas is a constant and we have a larger volume, we would expect fewer interactions with the walls, fewer bouncing off the walls. We would expect the pressure to decrease. So let's just see if that's what happens. We expect a lower pressure. So in this case, what's P2? Well, we can solve for P2. P2 will be equal to P1 V1, whoops, divided by V2, which will be 1 atmosphere, times V1, 0.500 cubic meters, divided by V2, which is 1.75 cubic meters. Divide that out, and we get that P2 is equal to 0.286 atmospheres. Now, if you want to leave it in atmospheres, if the problem doesn't state, then you can leave it in atmospheres. If you want to convert it to pascals, you can do that. But let's just take a look. We're going from 1 atmosphere to 0.286 atmospheres. What happened to the pressure? It decreased, just as we thought it would. Okay, very good. Let's take a look at another process. For process number 2, let's assume that the pressure is now held fixed. So we put some weight on the piston, and then we just leave that force on the piston. So whatever happens, maybe the volume will change, but we'll always have the same force being applied to the piston, therefore the same pressure. But again, we're still going to keep N constant. This is called an isobaric process. Baric as in barometer. What's a barometer? A barometer is something that measures pressure. So isobaric means constant pressure. Now, back to the ideal gas law. We have PV equals NKT. Now, we are holding N constant. K, we already know that's a constant. And we're holding the pressure constant. So those quantities that I circled, those are all constants, being held constant. Let's put them all on one side, and anything that can change, we'll put on the other side. So T can change. Let's put that over here with V. We'll divide both sides by T. So we have V over T. And divide both sides by P, and we have NK over P. Now, notice that everything on the right side, N, K, and P, those are all being held fixed. In other words, the right side is again constant, but if the right side is constant, the left side must be constant. So, no matter what we do, if the volume and the temperature change, the ratio of V over T must stay the same, because we know that equals the right side, and the right side is not changing. So what do we have now? We have that V1 over T1 must equal V2 over T2. There we go. And this is our relationship for an isobaric process. And this is referred to as Charles's law. Great. Let's stick some numbers in here. Let's imagine now we have 2.50 cubic meters of our ideal gas at negative 73 degrees Celsius. We then heat it up to 77 degrees Celsius. What is our final volume? Well, again, let's see if we can think about what's going to happen. We've got this volume at negative 77 degrees. We maintain the pressure, but now we heat it up. We heat it up, what's that going to do? That's going to increase the kinetic energy of the particles. The kinetic energy is going to be, the particles are going to be hitting that piston harder. What's that going to do? Well, if we maintain the same force, that's going to push the piston up further. The gas is going to expand. So we expect that V2 is going to be larger than V1. Well, let's see. Let's solve and find out what we get. Solving for V2, we'll multiply both sides by T2. We have V2 is equal to V1 over T1 times T2. In other words, V1 is 2.5 cubic meters divided by T1. T1, negative 73 degrees Celsius. Do I put negative 73 degrees Celsius here? No, remember, these temperatures have to be in Kelvin. So, negative 273 plus 273, that is 200 Kelvin. 77 plus 273, that is 350 Kelvin. So T1 is 200 Kelvin. T2, 350 Kelvin. Multiply those out, and we find that V2 is equal to 4.38 cubic meters. And we see that, yes, our gas has expanded. It's expanded not quite twice as much, but almost twice as much. Well, notice because our temperature has increased almost twice as much. Actually, 35 over 20 times as much, and if we were to figure that out and multiply by that, that's exactly what our final volume is. That ratio of the increase in temperature. Very good. Let's take a look at one more process. Our third process holds the volume constant. So again, keeping the number of particles, number of moles constant, we're going to now also assume that the volume is held constant. So imagine that we clamp this piston in place so the volume cannot change. This is what we call an isochoric process. Now, I'm not going to work this out. I actually want you to go through it and see if you can do it, just like we did for the isothermal process, the isobaric process. For a volume being held constant, do the same thing with the ideal gas law. Put everything that's constant on one side, everything that changes on the other, and see if you can figure out an analogous kind of equation like Boyle's law, Charles's law, that applies for an isochoric process. Okay? Give that a try. Now, what I'd like to do is take a look at this relationship between the energy and the pressure. How is this actually happening, and what does this really tell us about the energy, the kinetic energy of these particles? We have been talking about ideal gases. I now just want to imagine we're talking about a very specific kind of ideal gas, and that is a monatomic ideal gas. So that means we're going to assume that all of the particles in our gas are made up of individual atoms. Now, why is an one atom type gas going to behave differently than, say, a diatomic like hydrogen with two atoms? I'll come back to that in just a second. But let's just imagine that each particle, every particle of that gas is just a single atom. We've got all these particles moving around with some mass m and a velocity v bouncing off the walls. Well, by using the ideas we had talked about before with impulse and how the change in the velocity of a particle is related to the force, and that's related to the pressure, that along with what we know about an ideal gas, the ideal gas law, we can actually figure out what's the total amount of kinetic energy if we add up all the kinetic energies of the particles in the gas. It turns out that the total energy of the gas, which is all kinetic, remember we're ignoring any potential energy, the total kinetic energy, the sum of all the kinetic energies of all the particles, is 3/2 nkt. Now this is very interesting, this 3/2 nkt, and I'll come back to why it's important that this is a monatomic ideal gas. This is 3/2 nkt. It turns out that 1/2 nkt comes about from motion in the x direction. 1/2 nkt comes about motion in the y direction, and 1/2 nkt comes about from motion in the z direction. There's equal amounts of kinetic energy, so to speak, associated with the x motion, the y motion, and the z motion, to give us a total amount of energy of 3 times 1/2 nkt, or 3/2 nkt. If we had a more complicated molecule with more atoms, well, we'd have some energy actually in vibrational modes of the atoms, or rotational modes of the atoms. There would be other way that energy could be in those molecules. But with a monatomic atom, all it can do is be moving in linear directions, and that just makes it a little bit easier for us to deal with. So the total energy of the gas is then 3/2 nkt. It is directly proportional to the temperature. You double the temperature, you are doubling the amount of energy in the gas. Well, we know nkt, if we put it in terms of moles, that's the same as little n RT, or because nkt or nRT is equal to PV, we could also write that as 3/2 PV. So that's the total energy in the gas. Now, if we have n particles, we could divide by n and find out the energy per particle. But that turns out to be the average energy, because when you have a sample of gas, they're not all moving at exactly the same speed. Some are moving a little bit faster, some are moving a little bit slower, and it's a whole mixture. So what this actually tells us then is what's the average kinetic energy per atom. Dividing this by n, we get 3/2 kT. So that is the average energy per atom of the gas. Great. Now, we've got some ideas about energy and other properties of the gas. What I'd like to do is talk about some very, very general results about any kind of system. They're analogous to Newton's laws as far as mechanics goes. Newton's laws are to mechanics what our results are to the heat-related aspects of a system. They're called the laws of thermodynamics, and there are 4 of them. Now, just like Newton's laws often go by the numbers, Newton's first law, Newton's second law, Newton's third law, well, the laws of thermodynamics also go by their numbers. The first law of thermodynamics, the second law of thermodynamics, the third law of thermodynamics, and it's not the 4th law, it's actually the 0th law of thermodynamics. The first one that we're going to look at, the 0th law, is such a fundamental basic idea that it's kind of thought of as so fundamental it's called the 0th law as opposed to the 1st law. So we'll start out with the 0th law of thermodynamics and look at each one in turn.